In today's podcast, we're going to use Dalton's law of partial pressure to figure out the total pressure in a gas container that has more than one gas present. We're then going to use the moles of each gas present and the total moles present in the container to figure out the mole fraction of each gas. And we're going to look at the relationship between partial pressure and mole fraction. Dalton's law of partial pressure tells us that the total pressure that is in a gas container is the sum of the partial pressures of each of the gases that are present. So we can say that the pressure total is equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, etc., however many gases you have. It doesn't matter what type of gas is present. Again, why not? Because gases are mostly empty space. The size of the individual gas molecules doesn't matter. It doesn't matter if we have helium or xenon. The gas particles don't touch, and the gas volume is dependent upon the pressure and the temperature and the amount of gas present. So if we add up the pressure of each gas in an individual container and we put them all into the same container, the pressures add up. The example I show here, I have a blue gas, and you can see there's not many gas particles present. It doesn't have a very large pressure. The green gas has more gas particles present. It has a little bit higher pressure. The red gas has the most particles. The pressure is the highest. If I put them all into the same size container, the pressures are additive. The total pressure is equal to the pressures of each individual gas added up. Another way to look at that, let's talk about moles of gas. If I have 0.6 moles of H2, it exerts a certain pressure. And the picture here says that the pressure that exerts is 2.9 atm. In another container, same size, I have 1.5 moles of helium. More moles, higher pressure. The helium exerts 7.2 atm. If I put both the hydrogen and the helium in the same container, you can see we have many more gas particles and the pressure increases. The pressure total is equal to the two pressures of the two gases that are present. How would you work a calculation? If you knew the moles of one gas with the temperature and the volume, you could get the pressure of that. You calculate the pressure of the second one the same way. You add them together. To get the pressure of each, add them, you get the total pressure. Another way, add the total moles together with the volume and the temperature, you could get the total pressure. Another way that we measure gas concentration is mole fraction. We've done the mole fraction before, and now we're going to do it again. The mole fraction is the moles of a substance over the total moles present in the mixture. So if I have a gas mixture of hydrogen and helium together, the mole fraction of hydrogen is the number of moles of hydrogen over the total moles, the moles of hydrogen and helium added together. The mole fraction is related to the partial pressure. Mole fraction is a strange little X that looks like this. So the mole fraction of a gas is equal to the moles of that gas over the total moles present in the container. The partial pressure of the gas divided by the total pressure of the gas is directly related to the moles. The pressure exerted is directly related to the moles. So we can use the relationship that the mole fraction is equal to either the moles over the total moles or the partial pressure over the total pressure. It's a pretty nifty relationship. So let's work a sample problem. A mixture of 10 grams each of hydrogen gas, oxygen gas, and water are present in a 10-liter container. Calculate the partial pressure of each gas, the total pressure in the container, the mole fraction of each gas. Assume the temperature is 25 degrees C, which is 298, and the volume is 10 liters. There are a lot of different ways that you can use to solve this problem. I think that I'm going to first figure out the moles of each gas, and then I'm going to use the ideal gas law to get the pressure of each gas, and then I'm going to add them together to get the total pressure. And then to get the mole fraction, I'll just divide either the moles of each by the total moles, or I could divide the pressure of each by the total pressure. Either way will work. Let's figure out moles first. So I have 10 grams of hydrogen. Remember, hydrogen is diatomic, 2.02 grams per mole. So I have 4.95 moles of hydrogen. For the oxygen, I also had 10 grams. O2, also diatomic. I have a lot fewer moles of oxygen because oxygen has so much higher of a molar mass. So the partial pressure of oxygen is going to be much lower than that of hydrogen. And then for the water, the molar mass is between the two, so I'm sure the moles will be between the two. It's 18.02 grams per mole. So my moles of water vapor are 0.555. If you wanted to add that up, you would have 5.818 moles total. If you wanted to get the mole fraction using the moles over the total moles. Now I'm going to get the pressure. I know that PV equals nRT, so my pressure is going to be nRT over V. So for the first one, my pressure of hydrogen is going to equal 4.95, 0.08206. My temperature was 298, and my volume is 10. So my pressure of hydrogen gas is 12.1 atm. For the oxygen, the pressure of oxygen, we'll set it up the same way, 0.313, 0.08206, 298. You'll notice that I'm not using my units, but I know that they're the correct units. So my pressure ends up in atm. So this is 0.765 atm. And then finally, my pressure for the water vapor is equal 0.555, 0.08206, 298, again divided by 10. So my pressure of the water vapor is 1.36 atm. My total pressure, I can just add that up, and I get 14.2 atm. And then for the mole fraction of each, if I have the mole fraction of H2, that equals 4.95 over 5.82. It also equals 12.1 over 14.2. I can either use my mole over total mole or pressure over total pressure, and I get my mole fraction of H2 is 0.852. My mole fraction of O2, I'll just use the pressure this time, 0.765 over 14.2. So my mole fraction of O2 is 0.0539. And then finally, my mole fraction of the water is 1.36 over 14.2. And that equals 0.0958. Mole fractions always add up to 1. Recall percent composition adds up to 100. Mole fraction adds up to 1. And if I add together my hydrogen and my oxygen and my water, you'll find that the total is 1. So I used the amount of each gas to go to moles, the ideal gas law to use pressure, and then I divided the pressure of each by the total pressure to give my mole fraction, or the moles of each by the total moles to get the mole fraction as well. This problem states a mixture of 4 gases are in a 2.25 liter rigid container at standard temperature. The total pressure is 5.50 atm. The pressure of gas A is 1.25 atm, gas B is 1.75 atm, and gas C is 5 atm. What's the partial pressure of gas D? Well, I'll take the total pressure and subtract each of the other pressures to figure that out. What is the mole fraction of gas D? And how many total moles of gas are present? How many moles of each gas are present? So again, it's a partial pressure and mole fraction problem. So to get the total pressure, it said that it's 5.50 atm. If we subtract from that all of the other pressures, we have the pressure of A is equal to 1.25, the pressure of B is equal to 1.75, the pressure of C is equal to 0.50. So if we subtract that, we know that the pressure of D must be equal to 2.00 atm. The next question said, what is it in torr? So we have to convert to torr. 2.00 atm, 1 atm is equal to 760 torr. So if I convert that to torr, I get 1520 torr equals the pressure of D. What is the mole fraction of gas D? So my mole fraction of D is equal to the pressure over the total pressure. So that's 2 divided by 5.50. Remember, mole fraction is always going to be a number less than 1. It's 0.364. So it wanted to know the total moles. So I'm going to use the total pressure and the temperature and the volume to figure out the moles. We know that PV equals nRT, so N will be PV over RT. So the moles total is going to be the pressure total, which is 5.50 atm. The total volume was 2.25. R is 0.08206. And the temperature was 298, I believe. Nope, it's 273. So the total moles present is 0.522. Then it says how many moles of each gas are present. We can solve this a variety of different ways. You could use the pressure of each gas and the ideal gas law to get the moles of each gas. What I'm going to do is use the mole fraction as calculated by the pressure over the total pressure, and I'm going to multiply the total moles by that. The relationship I'm going to use, the moles of A over the total moles, which is 0.522, is equal to the pressure of A over the total pressure. That's our relationship between mole fraction and pressure, partial pressure. So the pressure of A is 1.25. The total pressure is 5.50. So in this case, we get that the moles of A are equal to 0.176 moles. I'll do the same thing for gas C. I know that the moles of gas C over the total moles are equal to the pressure of C over the total pressure. So the moles of C are equal to 0.201 moles. And the pressure are the moles of B over 0.522 is equal to the pressure of B, 1.75 over 5.50. And my moles of B are equal to 0.176 moles. And then finally, my moles of D over 0.522 is equal to the pressure of D, which is 2, over the total pressure, which is 5.5, and my moles of D are equal to 0.201 moles. I made a mistake earlier. The pressure of C is 0.0502 moles. Glad I caught that before I moved on. If 10 liters of oxygen gas react with 10 liters of carbon monoxide gas to form carbon dioxide gas, what volume of carbon dioxide is produced? Assume that the reactants and the products are at STP. What does that mean? 22.4 moles per liter. And also the reactants and products are at the same temperature and pressure, so we can use the balanced equation, the coefficients as mole ratios or as volume ratios. What is the mole fraction of each gas present when the reaction is complete? First thing we're going to do is write a balanced equation. That equation is 1 oxygen gas reacts with 2 carbon monoxide gas to form 2 carbon dioxide gas. And it says we're going to use 10 liters of each. I can look at this right now and see that carbon monoxide is my limiting reactant. Why? Because I need twice as much carbon monoxide as I need of oxygen, but I have the same amount. So my oxygen is going to be excess, and my carbon monoxide will be the limiting. So we want to know the mole fraction of each gas when the reaction is complete. So let's first figure out the volume of each gas when the reaction is complete, and then we'll convert the volume to moles using 22.4 moles per liter. So if I have 10 liters of CO, 2 liters of CO will require 1 liter of O2. That means 5 liters of O2 are used. We have 10 minus 5. That makes 5.0 liters of excess O2 when the reaction is complete. We'll do the product. 10 liters of CO, 2 liters of CO will form 2 liters of CO2. So we have 10 liters of CO2 produced. So at the end of the reaction, I have 5 liters of oxygen left, and I have 10 liters of carbon dioxide that I've produced. So let's figure out the moles of each. For my O2, I have 5 liters, and it's 22.4 liters per mole. So I have 0.223 moles of O2. And for my CO2, I have 10 liters, and we have 22.4 liters per mole. So I have 0.446 moles of CO2. I think I need to add another page. So my O2 is 0.223 moles, and my CO2 was 0.446 moles. So my total moles present in the container is 0.669 moles. So the mole fraction of O2 is 0.223 over 0.669, which is 0.333, and my mole fraction of CO2 is 0.446 over 0.669, which is 0.667. And you can see that they both add up to 1. Your mole fractions always add up to 1. So in this vodcast, we learned how the partial pressure of each gas present in a container will add up to the total pressure, and that the mole fraction of each gas, that's the mole of each gas divided by the total mole, is going to be equal to the partial pressure of each gas divided by the total pressure. Moles and pressure are directly related.